All right, let's get started. Welcome back, everyone. So today we'll continue the lecture that Eric started, or the module that Eric started last time on Bayesian Nonparametrics. So I had to reshuffle a little bit the schedule from here until the end of the class. So the last lecture is going to be on April 29th, but we'll have 2 lectures on Bayesian Nonparametrics. And as Eric mentioned last time, technically Bayesian Nonparametrics can be taught in a semester-long class. We're going to just compress everything and just give you some highlights within these 2 lectures. But let's start with a quick recap first, to see where we left off last time. All right, so Eric introduced this distribution over distributions, where the goal was to try to model the distribution over data, and we try to assume that, given all these points that we have here, we'd like to know from which subdistributions they potentially came from, right? And one way to do that is to introduce this mixture of, let's say, Gaussian distributions or mixture of components, where we have some finite number of mixture components k. They produce some sort of parameters, and then given the parameters, we can sample the actual points that we observe, right? So the question is now, like, how do we, well, we can do inference given this given this model, and we can assign every single point to the likely cluster that it came from, right? The question is, well, how many components do we actually need given a real data set, right? And if the data is streaming or data is coming in, can we somehow find new components if the data set is growing over time? And, well, one way, if the data set is fixed, we can just cross-validate and find k, right? But the other way that actually Bayesian Nonparametrics is trying to introduce is where we build a model that actually has potentially infinite number of components, and the number of components will grow with the size of the data, right? So basically what we do here, we just substitute this k with infinity, and we assume that there is potentially infinite number of components, and now we'll have this infinite mixture where we have a sum over an infinite number of sub-Gaussians, and every single sub-Gaussian is weighted with some pi, right? And the point is that given a finite data set, we know that every single point is probably came from a component, right? So since every single point came from a component, and the data set is finite, the number of components for the given data set is finite. But it could be random, right? Because we assume that there is some latent space of all possible components, and it's large and infinite. So then the question was, like, how do we choose prior? And we want to sort of preserve good properties of the prior of the standard Gaussian mixture model. And I believe Eric told you about the Dirichlet distribution, the properties, nice properties of the Dirichlet distribution, and then he introduced the Dirichlet process that generalizes the Dirichlet prior to the infinite number of components, right? And well, the intuition was that, or I guess the metaphor is that is so-called the Chinese restaurant process, where we have a restaurant, and we have a bunch of customers that are incoming, which are our data points, and we know that the customer that comes into a restaurant picks a table. And the next customer comes in and then picks one of the, either the table that was already occupied or maybe a new table. And then more popular tables, right, as indicated in here, have higher probability of attracting a customer. So more popular tables will have higher probability of being selected by the new customers, right? And then there is some base probability of actually not selecting any of the tables, but selecting some new table, right? So that was the metaphor that was introduced in the last lecture, right? And then to describe basically this process, we introduced this Dirichlet process that is given on the slide, right? And to be able to sample from this process, we can use this stick breaking construction, right? So we can represent this Dirichlet process exactly by this stick breaking construction. And then, so how we sample from this, we imagine that we have a stick that is of length 1, and then we're breaking the stick into parts, right? And so when we're trying to break the stick, we will first select a variable bk from the beta distribution, beta 1 alpha, and then we'll break the stick according to that. And then, again, we'll remove the fraction, this bk, from the stick, and then we'll produce the atom or the component that corresponds to that break. And then we'll recurse and keep breaking the stick more and more. So every following component would potentially be slightly smaller because it will be part or the fraction of the remainder of the stick. Right, so I believe, so just a quick recap of the process that I believe was already introduced in the last lecture. Right, so we have the stick. We go one by one, and this is the first break. We've broken it. We get some pi, or the weight, 0.4 in this case, and then we select the corresponding theta 1, right? And then we break the remainder. So we happen to break and get 0.5 of the remainder of the stick, and then we multiply it with the actual remainder size, and then we get 0.3 in this case, and we select the corresponding component, and then we keep recursing further and further, and then we get a bunch of components from the so-called base measure, right? That is the measure over these theta parameters. And on the left-hand side of the slide, you can see that this is how basically we sample this G from our Dirichlet process. So through this infinite recursion. So there are two constructions. So the construction that's just introduced was the stick breaking construction. And also, I believe Eric covered the Polias-Orn construction in the previous lecture, so we're not going to go into that, but the corresponding graphical models are given on the slide. Right? So now we know how to sample from the Dirichlet process, right? We know how to construct these samples. The question that we stopped at in the last lecture was, how do we do inference in this case? So given this Dirichlet process, this is given on the left-hand side, how do we do inference, also given the data set that presumably came from this Dirichlet process? And what do I mean by inference in this case? Or what do we mean by inference? Any guesses? All right, so by inference, we basically mean we would like to identify which components, in this case, the points came from, right? Or we would like to, let's say, answer queries such as what is the assignment, right, of all the points to all the clusters given whatever we observe, right? So for that, we need an algorithm that would allow us to do inference. And one of the algorithms that Eric already mentioned, but I think he rushed through it a little bit, was this inference through collapsed Gibbs sampler. Right? So the idea is that if we collapse or integrate out the measure, right, we would be able to actually come up with this distribution over, assignments for the nth point, given all the previous points, right, given the assignments of the previous points, and given the components from 1 to k. Right, so let's say we have our points, x1 to xn, and then we already assigned them somehow to cluster. Now let's pick a random point from there, and since the Chinese restaurant process is exchangeable, we can actually pick any of the points. It doesn't really matter. So we'll pick that point, and we can recompute the distribution of the assignments to the clusters for this point according to the equation given on the slide. So with these probabilities that are proportional to the counts and the likelihood of the point under the given component in the cluster, we'll select the corresponding component k, or instead of selecting one of the existing components, we can select one of the new components. Right? So how the algorithm actually works, and it's not given on the slide, but how it works, we'll start with random assignment. Maybe, we'll initially have a bunch of points here, right? And we'll assign all of them to a single cluster. Right? This is not a good idea because, well, maybe there is a better initialization for the sampling process. but let's say we assign them all to the cluster 1. Right. Now we can go and select, let's say, one of these points and try to recompute the probability of the cluster that it actually belongs to. So in our case, k is equal to 1, so it's either came from this big cluster that we just selected, or maybe it came from some other cluster, let's say k equal to 2. So there is a probability, or non-zero probability, that we can compute exactly if we have a conjugate prior for the likelihood, right? And select a different cluster for this point. So what would happen, basically, this point will break out and will form its own cluster. Now we have another point. So we can repeat that for any point in the data set. So then we'll select another point, maybe here, and then again try to resample the zk for that, the zn, sorry, for that point, and then it could now select from one of the two clusters, or maybe break out to the third cluster. Right? So that's how the algorithm would work. So we'll keep iterating over all the points and then trying to assign the cluster to them. And then eventually, this is a Gibbs sampling, right? It's Gibbs sampling procedure. It's a Markov chain Monte Carlo. So after some burn-in number of steps, we'll say that the samples, or these vectors of z1 to zn, will be the actual cluster assignments coming from the posterior distribution that we're trying to sample from, right? So eventually, let's say we'll get z1n initial, and then eventually we'll get z1n at time point t, and starting t, we'll just collect all the other, let's say, capital T of samples, and these capital T of samples will represent our posterior distribution. So there are some problems. So this is a very simple algorithm. Given a likelihood and conjugate prior, we'd be able to compute these distributions exactly, but there are a few problems with this approach. So one of them is that we have to update one data point at a time, right? We select one of the data points, we go and update the cluster for that data point, have to condition on everyone else. This is problematic. Imagine we have 1,000,000 of points, and just to make a single pass through the 1,000,000 of points, we will have to repeat the same procedure 1,000,000 of times. And that's just a single pass. This is just a single sort of Gibbs update. So it's, if the initialization was bad, right? If the true clusters are somehow were merged initially in a single cluster, so the way that I just introduced you, right, the way that I described it, we'll start from a single cluster and we'll try to break points out one by one. So in this case, it will take very, very long time and very, very large number of iterations to try to get the actual cluster assignments. So since the distribution is sort of infinite, and if we have a large number of points, perhaps the number of clusters is pretty large. But if you recall, the stick breaking distribution has a bunch of pies, and a lot of these pies have a very low probability, right? So there is a bunch of clusters that have a very, very low probability, and we still want to be able to select them. So in order to be able to select them, we'll have to do this Gibbs sampling procedure and to mix well. So again, that would require a lot of iterations. If the likelihood is non-conjugate, we'll have to somehow approximate that integral that I told you that it's easy to compute, but if it's non-conjugate, it's going to be hard. There are some improvements to this algorithm, so you can look up the paper from Radford Neal. But we'll try to look into an alternative right now. Right? And an alternative would be, instead of trying to collapse the random measure, we would try to actually instantiate it, right? We'll try to instantiate this latent measure and assume that then it is given. So here is another inference algorithm. It's called block Gibbs sampler, right? So instead of trying to integrate out G, we'll try to get it, or sample it basically from the Dirichlet process. The problem is that G is infinite dimensional. Right? So we are not able to represent the sum over all possible components with weights exactly. And the simple solution to this would be just truncate it. We know that all these weights, all these pies, eventually will anneal to pretty much zero because of how the stick breaking process works. And In fact, we can assume that there is some large k, let's say 1,000, and bk, b,000 in this case, we'll just set it equal to 1. So what it means is that pi 1 to this pi 1 to pi 1,000 will be some weights, but let's say pi k plus m, where m is some number that is greater or equal than 1, will be actually equal to 0. Right? So why is it actually going to be equal to 0? Because of this term. Because 1 minus bk will be equal to 0, so we'll just pretty much zero out all the components starting from capital K. Right? So we truncate our stick breaking process at some predefined number of components. So in this case, how can we sample? Right? Given a fixed number of components, now for every single point in the data set, we can sample this assignment probability of Zn equals to k as proportional to the joint probability distribution. So this pi k were pre-computed at the previous step, so given this k clusters, and then we'll be able to compute a bunch of these terms and then renormalize them and then sample Zn equal to k from this renormalized multinomial distribution. And then to actually estimate pi k, we're just going to follow the stick breaking process, right? So we can think of a stick breaking process as just a sequence of binary decisions, and in this case, it's a truncated sequence of binary decisions where we go all the way up to the kth component. And then after we resampled the z's, we'll have to go and update this bk's, right? So by using the stick breaking, process, we actually introduce this b variables that are latent random variables, right? So as in any MCMC kind of procedure, when we are trying to integrate out some of the variables, we'll just jointly keep sampling them. And in this case, we're going to iterate between b's and z's. Any questions so far?
Sorry if I missed this, but how do you choose what's a good value of k?
Right. So in this case, we want to build a process where you don't have to choose the good value of k. So in the previous algorithm, you didn't have to choose, right? We just integrated this out, would go and just resample, and eventually through this breaking out procedure, where we occasionally would sample k plus 1, right? Points will just spread out across the clusters and eventually will equilibrate somewhere, right? So in this case, we assume that, well, there is some k, let's just randomly select it, and then hope that this would approximate our process to some extent, right? But that's a good point. So if we do fix k, it's no longer a Dirichlet process, right? It has some sort of bias, it has some sort of error, and it's incorrect. But even if we're okay with this error, we can use this efficient block Gibbs sampler algorithm by iterating and resampling the two blocks of two variables, right? And then in order to recompute this bk's given everything else, we're going to sample it from this beta distribution that all only depend on the counts, and the counts are coming from the counts over the z variables, right? Okay, so let's now improve that a little bit more. So the problem was that by truncation we introduced some sort of error, right? And we would like to somehow get rid of this error. So how do we do that? Well, one idea is instead of using a fixed truncation at k, and then where we have to sort of predefine this, we can introduce another random variable that would indicate where we truncate the process, right? And then we'll marginalize out this random variable, and we'll arrive at our original Dirichlet process. So this is the idea. So how do we do that? So we'll introduce a uniform random variable, which is called un, which will be introduced for every data point, which is important. Okay? And then we're going to sample zn's, or the indicators for every single point, according to this distribution, right? Where I is the indicator of whether pi k is greater than un. So given a fixed un for the data point n, we can compute this thing, right? And then it will be either 0 or 1, because it's a binary indicator, and then we can multiply it with the corresponding likelihood. So this posterior distribution would be sort of proportional to that. And so the idea is that by introducing this un and fixing it for a given point, it will sort of select a finite number of components that we can sample from. Right? So here's the intuition. So let me draw it right here. Remember that we had this pi k's. So let's say this was pi 1, this was pi 2, pi 3, etc. So all of these pi's, all of these weights had some sort of magnitude. So when we sample un and then try to select pi k's, only those pi k's that are larger than this un, so basically we are sort of slicing these bars, right? And now what I'm saying, let's say this is un, it means that z and k, right, can be only equal to either, in this case, 3 or 1, right? Because the probability of selecting pi 2 will be equal to 0, right? So given a fixed un, and even if we have the infinite number of these components, after slicing, those that are non-zero are going to be are going to be finite. So it's going to be a finite subset of these components. So now, how exactly are we going to sample these UNs? So given a data point and given a current assignment of the data point to one of these components, we're going to introduce this distribution that is uniform from 0 to pi zn. So let's say that my point xn was assigned to cluster, let's say, zn that is equal to 3, right? Then, again, our example with pi 1, pi 2, pi 3. So in this case, basically the upper bound for the uniform from which we're going to sample is defined by this boundary. So this is going to be our un, or the upper bound for the un. And then we are going to sample one of the, so a un somewhere in this interval, right, in this band. So after we sampled un here, so let's say we happen to sample it on this level, we will be able to compute, we'll be able to compute this probability of z n equal to k according to this slicing, as I introduced in the previous slide. Okay. All right. So after we again resample this z and k's according to the slicing, so we do this for every single point. We have a new assignments, so z1 to zn, and then for these new assignments we can recompute again bk's, right, the stick breaking proportions, and then again recompute the pi's as we want, right? So know that in this case we only need to represent a finite number of components, right, that is given here. So given un for every single data point, we'll have slightly different but finite number of components. And the good thing is that it preserves the structure of the block sampling, right? So even though blocks are going to be slightly different for different points, we're no longer doing like everything in parallel for every point and then select all the z's and then go and select all the b variables. Now they are slightly different because we have to resample these uns for every single variable in the data set, but we still are able to iterate between the two. It's not as slow as, you know, where we had to integrate out the entire measure and then we had to do point by point in the entire data set. So any questions about the slice sampler? No questions? Okay, so this was the inference part for the Dirichlet process. Now we're going to move on to the topic models, right? So we've covered already topic models in the class. And the idea behind the topic model is that we have some collection of documents, and we assume that every document is some sort of distribution over features. Every feature is a distribution over words, in this case. And then the document is represented as a collection of words. We don't care about the structure between the words. We care only about the counts of the words. So this is a so-called bag of words assumption. And then we assume that words within a document are distributed according to a specific mixture model, right, that is coming from these features. And each word in a document is associated with a feature. So the feature, or this thing that I call feature, is eventually going to be called topic, right, in this topic model. Because when we fit the model to the collection of documents, we'll see that certain words that are coming from the same features are sort of clustered according to the topics. So we can associate some sort of meaning or topic to the corresponding feature. Right, so in the latent Dirichlet allocation, that represents our topic model. So the sampling process goes like this. We start with, let's say, we predefine the number of topics that will be equal to k. We can sample these topics from the Dirichlet distribution as every topic defines a distribution over words, right? So we sample k of those, and then for every single document, we're going to iterate and sample a distribution over topics first, and then from this distribution over topics, we're going to sample words, right? So it's a sort of hierarchical sampling procedure. So the question is, how do we determine the number of topics? It's pretty much the same question as with the mixture model, right? Should we select it a priori somehow, or can we somehow determine it automatically? Right, and the idea is to try to construct a topic model with infinitely many topics. Right, so we had this Dirichlet distribution or Dirichlet prior on the topics, right? The distribution over the topics for a given document. Now, instead of using the Dirichlet distribution, we can actually go ahead and substitute with the Dirichlet process. So the heuristic is very simple. So let's say you have a Dirichlet somewhere in your model. Maybe it's a more complex model than a topic model. Maybe there are some mixture components. And then you don't know what is the k, right? You would like to determine what is the k. So one way is to go and to cross-validate. If you have a fixed data set and you care only about this data set, if you have a lot of data and you know that your data will grow over time, maybe it's worth trying to take a Dirichlet process and substitute your Dirichlet distribution within the model with the process. So the substitution is simple. The corresponding inference algorithms would require some sort of thought, and as well as learning. So another problem that arises here when we do this substitution is that we would like the topics to be shared across the documents. And this, as we'll see, it will become a bit problematic in this case, because whenever we sample these infinite components, every time we resample this mixture of infinite components, because the base measure is continuous, right? We perhaps will be selecting all the time different components. So let's say given document 1, you go and sample an infinite mixture of potential topics for that document, and given a document 2, you'll go and resample this infinite mixture of components, but the components might be slightly different because we can't guarantee that the components are going to coincide, right? So so if we have m independent samples from a Dirichlet, right, we know that the number of topics is fixed, and we know that in the end of the day, all the documents in our corpus are going to be sharing these topics, and the learning, or basically the point of the model is actually in sharing, right? Because if all the topics are different for all the documents, then there is no point of trying to infer the meaning of the topics, because for a new document, you're going to infer a completely different set of topics. You will not be able to relate it to your, let's say, training data. So let's see. Right, so this is what I mentioned, that the Bayes measure in the Dirichlet process is continuous, and therefore the probability of selecting exactly the same topics for all the documents is going to be equal to 0. So any questions about that? Right, everyone is clear why this is problematic. Right, so how do we go about fixing this? Well, instead of continuous measure, instead of allowing sampling parameters from a continuous space, if we had a discrete measure, as in the initial topic model, like here, right, we'll constrain ourselves to always select topics from one of these k components. But if we want to have, so this will encourage sharing, right? If we want to have an infinite number of components, we would like to have an infinite and discrete Bayes measure. So now, if we have an infinite number but discrete number of topics, we'll not suffer from this problem where we slightly perturb and can select some topic that is slightly different but still not exactly the same. And because we would like to have an infinite number of topics, we also would like to be able to randomize over these locations, right? We don't want to have just infinite, discrete, and fixed. We'd like to have infinite, discrete, and random Bayes measure, right? So these are the properties we would like to have in our model. And well, there is a solution that EYT and others proposed in this paper in 2006. So note that when we sample something from a Dirichlet process, right? We sample a distribution from a Dirichlet process, it actually is a discrete, infinite, and sort of random measure. So when we get a sample from a Dirichlet process, it will be a bunch of spikes on our, line of parameters, and the weights that we assign to them are going to be random, but the positions are going to be fixed. So if we use this sample from the original Dirichlet process as the Bayes measure for another Dirichlet process, we basically satisfy the properties that we just described. Right, so if we sample this G0, and then we're going to use it as a Bayes measure in another Dirichlet process, we can go sample G1, G2, and etc. GK for all different documents. And we guarantee that the topics, because they were fixed after we sampled G0, are going to be shared across all of them. There's going to be an infinite number of topics, and all of them are going to be shared. And if we resample the whole thing, right, these spikes here are going to shift left and right. And so they are not fixed for every instantiation, but if we resample the entire thing, they might change. So the metaphor for this process is this Chinese restaurant franchise. Right, so to describe this, imagine a franchise of restaurants that all serve food from an infinitely large menu, but the menu is global for all the restaurants because it's a franchise, right? So they have to have some sort of established global menu. So again, each table in the restaurant, and we didn't have in the Chinese restaurant process, it orders a single dish, right? And then we'll have this nRT, will be the number of customers that we have in a restaurant R at table T. We'll have mRD, the number of tables in a restaurant R serving dish D. And we can also count the total number of dishes D that are served across all the restaurants, right? So this would sort of determine the popularity of a dish across the entire franchise of restaurants. And so again, given a single restaurant, a customer enters a restaurant and picks a table, and then the next customer that enters the restaurant again picks a table according to the distribution that we have here, right? And the only difference is that we also introduce this, dish selection process, right? That each table also gets a dish, and there is a probability of selecting a dish for a new table. So whenever a customer decides to sit on a new table, that table will order a dish for the customer. So the probability of selecting that dish for that table across all restaurants will be proportional to the popularity of that dish, Similarly, as we had this probability of selecting a table by a customer to be proportional to the popularity of the table in terms of the number of customers, same thing happens with dishes. And let's say table 1, when it was created, got one dish, table 2 got the other dish, table 3 got, again, the same dish, and it happened to be more popular than the first one. So again, dishes are sort of global in a sense, right? They are provided by the franchise, and then their popularity is, again, global across all the restaurants. So from a graphical models perspective, again, we recall that we have this representation for the Dirichlet process, this stick breaking and Paula's Orn representation. Once we go to the hierarchical Dirichlet process that I just introduced, on top of our measure, we put another measure that comes actually from this from the base measure that is continuous, and then the inner measure now comes from the base measure that is infinite, discrete, and random. Right? Any questions? Any questions about that so far? Right, so how do we go about building this infinite topic model with this hierarchical Dirichlet process that I just introduced? So our metaphor for restaurants is actually equivalent to documents. Like all the restaurants are different documents. The dishes are the topics, right? The popularity of the topics across the documents is shared. Therefore, it's pretty much the same as this shared global menu of dishes. So we start with a v-dimensional distribution, so we can sample h from that v-dimensional distribution, where v is the size of the vocabulary of words. And we also, by the way, we assume that the vocabularies are the same across the documents. And then we can sample the global distribution over topics, right? Or, if you will, like the global distribution over the popularity of dishes in the menu in the Chinese restaurant franchise. And then for every document M, right, we're going to sample first the distribution over topics, which is going to be an infinite distribution. It's going to come from a Dirichlet process with a base measure that we just sampled beforehand. And then for every word in the document, we're going to sample first a topic, and then after we sample the topic, we're going to sample the word from that topic, because every topic is a distribution over the words. So recall that in the mixture model that we had, so basically the difference is this very last part, where instead of sampling a discrete word, we used to have our Gaussian mixture components, so we would sample these x's from the Gaussian with the corresponding mean and covariance matrix. Right? So technically, we could have a hierarchical Gaussian mixture or hierarchical Dirichlet Gaussian mixture model. All right, so this is a graph from the HDP paper, and why basically it answers this question: why is this important? How do we select k, for example? Right. So that's one of the questions that you asked. And if we were to use the standard LDA with a fixed number of k's, where on the x-axis we have this number of topics that we pre-select, and then we take our LDA with pre-selected number of topics, we go and fit it, and we get the likelihood of the data under this fitted model, and we get some point on this curve. So we have this blue curve that corresponds to LDA with different number of topics, and we see that like some numbers of topics are sort of suboptimal, right? And at some point we get to this like optimal region where, you know, from 50 to 80, this is the optimal or almost optimal number of topics for the given data set. And then afterwards, maybe there is some sort of suboptimality here because the topics are too many, so that affects the likelihood a little bit. But if we run an HDP mixture, in this case, it doesn't really matter. So HDP mixture is able to determine automatically the number of topics. We do have to fine-tune these parameters alpha and gamma, but so after we learn them, we can quickly arrive at a model that automatically determines the number of topics. And on the right-hand side, you have this posterior distribution over the number of topics in the HDP mixture. And so this is the posterior distribution that it inferred. Okay, so any questions at this point? So we're not going to go into details of how to learn HDP or how to do specifically inference in this hierarchical model. I encourage you to look into the original paper. Yeah.
I'm just curious, how robust is the approach to the sampling? So is it the case that as logically it will always be the same on all the problems?
I guess in comparison to LDA, as long as the assumptions are the same, asymptotically, yeah. Yeah. So if you run the inference and then you run MCMC for a long enough time, you should arrive to a pretty good posterior distribution. In terms of efficiency, it's hard to comment. So I never worked myself on HDP, so we have students in our group who worked on that. I believe there are efficient ways that allow you to do sampling from the posterior very efficiently with Markov chain Monte Carlo. But yeah, in terms of sample efficiency or in terms of like sensitivity to parameters, you eventually, if you run an MCMC type of algorithm, you'll eventually arrive to the actual posterior. But again, eventually is very is not a precise term. Right? Okay, so if there are no questions, let's move on. So now we looked at simple mixture models and we looked at the LDA model, right? And then we started with the Dirichlet distribution. We extended it to Dirichlet process, and in these cases, right, we wanted to sort of cluster the data in non-overlapping clusters. But you know, the problem is that in mixture models, you know, DP or Dirichlet, right, we will not be able to share features between the clusters, and in many applications we would like to actually share the features, right? For example, you know, we have a bunch of a bunch of latent features. For example, objects that we have in the image that sort of lead to the pixel values, right? Given a bunch of objects, you take a picture of that, you get some sort of pixel values for your image. So these objects jointly sort of generate the scene together. So therefore, all of these like latent objects, in some sense, generate the pixel values of the image. So we would like to be able to account for this sort of joint effects. Or, for example, actors in social networks, you know, belong to multiple social groups. So you don't have to have, you know, a very specific, or you know, a single social, or movies contain aspects of like multiple genre, right? So in latent variable models, so the latent variable models allow us to, you know, exhibit this multiple feature property to various degrees. And here is one example. Let's say a very simple linear, or very simple factor analysis model, where our observations are related to some sort of latent features A through some linear transformation with a matrix W, right? Where we have data point specific weights that are assigned to every single latent feature, and we have a bunch of latent features, and there is some sort of noise vector epsilon. And another example is LDA, right? Where we just discovered that you know, every single word comes from a mixture of topics. Therefore, with some different proportions or with some different probabilities, this word might have been generated from the corresponding topic in the given document. And so it's like mixed sort of membership models, or types of mixed membership models. But in this case, let's look a little bit closer at actually the first example with the factor analysis. Right? We had this let's say we have a k latent features that are represented by these a's, and then we know that for every example we have some sort of combination of these features, and this combination in this case that is given on the slide is linear. It could be convex, it could be something else, but what if we want to have, again, an unbounded number of possible features, right? We would like to, so if the data set is growing, potentially the k, or the number of features that we've discovered maybe in a portion of the data set, is not enough to sort of explain the rest of the points in the data set. Maybe there are some latent features that are not observable in the initial few points in the data set, but maybe as we go and observe more and more images, we'll discover that there are more and more possible objects that could be in the scene, right? So in this case, we can use, or the question is, right, can we use the same Dirichlet process check and apply it to this simple factor analysis model? And the solution is, well, we can allow infinitely many features a priori, and then again, given the data set, a random subset of these features will be selected, and we can do, again, inference. But in this case, we would have to have this W or A have infinitely many rows or columns correspondingly, right? If we have infinitely many features, it means that we'll have to have so many different columns. Where are we gonna store all these features, right? We can't represent infinitely many features in this case. So we'll have to solve this problem. So the solution is we can assume that our infinite matrices are very sparse. So in expectation or in the limit, even though there are infinitely many rows or columns, the non-zero elements in these rows and columns are actually, the number will eventually converge to some finite number in expectation, right? So the more and more columns we observe, the sparser and sparser they would be. So eventually, like in the infinity, basically, all the columns or the corresponding rows are going to be zeros because all the features that we've observed are just become sort of non-effective. And this construction, or this assumption was introduced in this paper by Griffiths and Garamani that introduced this Indian buffet process that I'll describe in just a second. So first of all, let's recall that we had this Chinese restaurant process, and we could imagine that actually Chinese restaurant process also defines a distribution over, it defines the distribution over partitions of the data, but you can also represent it as a binary matrix, right? Where every single row would correspond to a customer, and every single column would correspond to a table, right? So these are going to be different tables, and these are going to be different customers. Or more broadly, we can say that these are different components or clusters in the mixture component, and the other ones are going to be our data points. And what happens also, know that every single row has a single non-zero component in the matrix. Right? So this is the mixture model. More generally, we would like to be able to have more non-zero components per row. So maybe every single element in the data was generated by a bunch of latent factors, but we know that the matrix, our assumption is the matrix is sparse, so the number of latent factors should be small. It can be very large. So how can we represent this in the factor model? Well, we'll say that our matrix that corresponds to the mixture weights that are assigned to the latent components A are represented as this like sparse matrix Z multiplied by some matrix V. And we can assume that the sparse matrix Z, or every element of the sparse matrix Z, is sampled according to the process on the slide. So first we sample this pi k's from some beta distribution. So for now, let's fix k. Okay. So if k is fixed, pi k is sampled from this beta distribution, and then z and k so for basically for every, so this happens for every row, and this happens for every column. So given this pi k's for every single row, we're going to sample z and k IID from these Bernoulli, the corresponding Bernoulli distributions. So in that case, we can write now the distribution over the Z matrix, right? So we know that it is IID across the rows. We know that it's IID across the columns, and then inside here we need to integrate out the pi k, because pi k is our latent variable in this construction. And if you do the math, eventually you will arrive to this distribution, and then mk is basically the column-wise sum over these indicators, right? So by construction, again, this distribution is exchangeable. It doesn't depend on the order of rows or columns. So we've made the corresponding assumptions to ensure that it is the case. So the question is, how is it sparse? Right? Or is it going to be sparse? Because by assumption, we wanted to have it sparse. So in fact, I'm not going to derive or answer this question. So, but if you sort of analyze this distribution, you will note that the probability of getting a very, very dense matrix would be pretty small in this case. So you will not have like all your elements in the matrix equal to 1. Okay, and as k goes to infinity, basically the sparsity pattern will be preserved. So the larger the k, the larger the number of 0 elements will be in the matrix. Right, so one way to extend this to our infinite case is to take the limit to infinity. So basically have this representation, say, let's start with some k, and then let's say k goes to infinity. So what will be the limiting distribution of that? And as k grows, well, we'll have more and more columns, as I mentioned, that are going to be empty or almost empty. And we don't want to actually represent an infinite number of like almost empty columns, right? So for that, Griffiths and Garamani define this equivalent class called Z in square brackets. Or basically all matrices, since all the columns are exchangeable and all rows are exchangeable, technically you can sort them. And you can have all the initial columns are as dense as possible, while the other rows, you can ensure that the other rows are going to be sparser and sparser and sparser, right? So if I give you a matrix, you can technically sort it according to this procedure, or it's called left-ordered binary matrix, which is the equivalence class. And if I give you two matrices that are seemingly different but have pretty much the same patterns, after sorting, if they are equivalent, these two matrices are belonging to the same equivalence class. Right, so instead of trying to represent this distribution over z's, they try to represent the distribution over the equivalence classes. And here's an example from the paper. So on the left-hand side, you have this matrix that was sampled from the distribution. After this left ordering procedure, we'll basically get the pattern on the right. And you see that the columns are getting sparser and sparser as we go from left to right. Okay. So we'll introduce, right, so all the matrices within the equivalence class are equiprobable, right, because all of them are coming from the same equivalence distribution, and by construction, they will have the same probability. Question?
So we're using the fact that the rows basically, the columns end up being 0 in those kind of strong sense, like the probability that it's going to end up being 0, in a sense stronger than the probability.
Right.
Because says if you choose convergence of probability, then you're going to end up with
Right, right.
So this is a very strong form of convergence.
So you're saying the form of convergence of the probability of non-zero elements in every single column is going to converge to 0 in probability or something? Sorry,
This might be technical, this might be better offline, but I'm just saying that it's not just that it's converging in a very strong sense.
Oh, I see. The strong sense of convergence. Yeah. Right. So going back to what I was saying here is that we have these equivalence classes. All the elements within the equivalence class are equiprobable, and right. So we can define these vectors like z, 1k, 2k, etc., and minus 1k, and this will be the history of feature k for the data, for the corresponding data point from 1 to n minus 1, and this will be the history for the data point n in this case. And then we'll let this kn to be the number of features that we have in the history h for the corresponding data point. Right, so we can actually show that the total number of this left-ordered equivalent matrices in Z is equal to this expression on the right. So it will be choose k from this number. Right. So this allows us to slightly rewrite the distribution. I'm not going into the details or math here, but the idea is that we can write and represent this distribution over the equivalence classes. And we know that all of them are equiprobable. We'll just sum over all the elements of the equivalence class, and we'll get the corresponding probability distribution over the equivalence class as an element. And then after that, we can take the limit. Right? We can take the limit of k and let it go to infinity, and see how this probability distribution would look like. Right? So this is the expression from the previous slides, and then we just take k, go to infinity. We'll just copy over the terms. This term will stay the same. The next term will turn into 1. This term should be familiar to you from analysis, from the standard analysis, which will turn into an exponent, right? And then we copy over this term here, and again we'll get just a bunch of factorials, or the factorial ratio. So, but this sort of defines our distribution in the limit, right, over these equivalence classes of these binary matrices. So the corresponding process that was introduced in that paper is called the Indian buffet process, and we can describe, or through an analogy or another metaphor, as follows. So we have customers that are entering, again, a restaurant. In this case, it's an Indian restaurant, and they are presented with a buffet, or pretty much like infinitely large buffet. And the customer helps themselves according to a Poisson process over the dishes, right? So the customer would go and try a dish with a probability proportional to the Poisson process. And let's say the first customer tried these 2 dishes initially. The next customer comes in, and then the customer will try the dishes that were already tried with higher probability, and potentially also with some probability, right? The customer will sample new dishes. Right, so again, and then the next customer comes in, and the first dish happened to be the most popular, so it was tried by everyone. And then the next customer also tried the dish of the second customer, and then also sampled something new. Right? So the dishes that become more popular over time are more probable according to this construction. which reminds some sort of the matrix or the equivalence class of left order matrices that I just told you about, right? So if you look at the matrix here, you'll see that the first column is not sparse at all, and then the second column maybe is sparser, and then on average, your columns are going to get sparser and sparser. So there will be some sort of some dishes that were tried maybe by one customer, but no one else ever tried that dish, just because the probability of selecting that dish was much smaller for, let's say, the nth customer after having selected, after the first n-1 customers selected the first few dishes. Any questions about the construction? Right. So this is the example of this process, sampling this matrix and then left ordering it. And so there is a proof that Eric has on the slides for for basically computing the probability that the probability of the matrix that we introduced, the probability of the Z matrix, is correct under this sampling distribution. So I'm going to skip through that, but you can take a look at the paper or at the slides later on. So what are the properties, again, of this IBP process that we just introduced? So the properties are that the most popular dishes or the most popular components in our factor analysis model are going to be more popular over time. So they will have much higher probability of being selected. The number of non-zero entries in every single row will be distributed according to Poisson. That's how we define the process. And this is due to exchangeability. We don't really care in which order the customers are entering. The sampling process for dishes stays the same. So due to this property of the Poisson process, that if two variables are sampled from two different Poissons, then the sum of the two variables is sampled from a Poisson over the sum of the corresponding A parameters. Then we can say that the number of non-empty columns, and by non-empty columns I mean that we just try to see which columns don't have at least one, or which dish basically was selected at least once, right? Will be distributed according to this Poisson AHN, right? So IBP can be used to build this latent feature models where the number of features is infinite, and just using this construction and sampling the Z matrix and then multiplying it with the corresponding weight matrix, we'll just arrive at our factorial model with an infinite number of components. Question? Okay. So maybe a few more takeaways. So we've covered in this lecture and in the past lecture was how we basically started again from a Gaussian mixture model. We assume that there is a k components, and then we try to sort of remove this limiting assumption of k. Instead of trying to cross-validate, we try to introduce a proper probabilistic process, right, over an infinitely many components, infinitely many topics, or infinitely many factors, and then construct a proper probabilistic model that allows us to do inference and learning in it. And we noticed that, well, one of the trick that we had to use in all of these processes is, in defining all of these processes, like to use this property of rich gets richer that allows us to sort of manage the complexity. So even though the number of clusters or components or latent factors is infinite, only a small subsample of those is going to be highly probable, right? I guess I'll stop at this point and see if anyone has any questions. Okay, so in the next lecture, we're actually going to go into the Gaussian processes. So all of these so far were used for clustering kind of models or unsupervised learning, right? Latent Dirichlet allocation or let's say mixture models. And the Gaussian process will actually try to learn discriminative models or probabilities over functions that try to predict some quantity y given some x's or some inputs. Okay.